Hello everyone, Namaste. I am Ramnath who would like to present you the series on key learnings from chip development. This is part 12, which is a continuation of part 11, and this is on synthesis of RTL design, where I will be covering mainly on the aspects of why synthesis doesn't infer when it is related to CDC or RDC synchronizers. We will also briefly discuss on the ASIL aspects. We will give preliminary details on these aspects only. However, more details and information can be obtained from the references available on the net and from good books. Thanks for learning along with me. Feel free to provide your suggestions. This slide basically explains the synthesis and various inputs involved in it and what are the various steps performed. Okay, we'll now go through detail into this one, which is already covered in other parts. Out of the 10 items presented here, we have already covered the first three, and we will be discussing more on the CDC or RDC synchronizers aspects, why they are not inferred by the synthesis tool. CDC stands for clock domain crossing. RDC stands for reset domain crossing. So these are all asynchronous signals which transfer from one domain to another. When they are crossing, we need to add synchronizers to stabilize the signals, and we'll discuss why synthesis tool doesn't infer these, even though some information about that is known. We will discuss more on CDC, RDC, and the ASIL aspects also over the slides. Usually, a SOC design will contain more than 50 or 100 clock domains. Similarly, a different number of RDC domains based on the scenarios. So here we will briefly discuss on the different aspects of the CDC. Okay, here if you see, this belongs to clock 1 domain. This belongs to another domain called clock 2. So similarly, for many clock domains may exist. So if you see this transaction, this flip-flop is transacting with another flip-flop in the same clock domain, and this signal transfer, when it is happening, there are no synchronizers needed because both clocks are operating at the same clock one. In the same way here, the two flops are operating at clock 2, and the signal transfer, whatever is happening here, they are operated at the same clock 2. So you don't need a synchronizer in between. So, however, if you take this signal transfer from one clock domain to another clock domain, such as this one, then we need some additional uh, signal smoothing, because this is an asynchronous signal. If you see here, this asynchronous signal is being sourced from clock 1, and the origin destination is happening at the clock 2. And if the clock 1 and clock 2 are generated from two different clock sources, then you need different, then this signal becomes an asynchronous signal. Hence, you need a synchronizer. This is called clock domain crossing, because it is crossing from one clock to another clock. That is why, to stabilize this asynchronous signal which is originating from here, you need a synchronizer. Then you will be transacting and giving it to a synchronous signal to this clock domain flip-flop. Okay, so this action is performed by a synchronizer. We will figure out why this whole thing is needed. Okay, for this purpose I will take one some old time example which is very relevant in this case. So you guys know Atithi is a perfect example of an asynchronous signal. Atithi means like a guest. But if you see actually a tithi means actually it related to some concept wherein it is a fundamental concept in the Hindu calendar system that follows a lunisolar system which considers both the sun and the moon time. This tithi has an average time period of 23 hours and 37 minutes, and its actual time varies from 19 hours to 26 hours. So that means like we will know that why this concept will be more related to asynchronous signal, we know. So usually in the olden days, people were not coming at specific time to the home. So they, since they were not following some specific tithi, they are called atithi, which who do not follow tithi are called atithi. So this asynchronous signal also is not following specific time constraints which this clock 2 domain corresponds to. So if assume that this Atithi comes, assume that for lunchtime, he will come at before time only and we will join the family. Then the householder has enough time to cook food and then will be able to serve on time in a rightful manner. However, assume that, and even in the same case, this asynchronous signal which is coming on time, giving enough setup time for this clock with respect to this clock, and enough hold time with respect to this clock. Then this flip-flop also will be able to process it properly. But however, sometimes no, if this Atithi is coming exactly very close to their lunchtime, then the house owner doesn't have any time. So the house owner will not be able to honor and treat the guest, this Atithi, properly. That same thing is happening here. So this asynchronous signal is coming, and hence what they do is like, for simplicity's sake, I want to mention like how it will be done and all. So there will be a guest room and a dining room. Consider that this is a two parts. Okay, so then in the guest in the hall or veranda where the asynchronous signal will be processed. That means like they will be asking some questions to the Atithi. How are things going? What is that? Where is the occasion? And all that they will be taking. During this time, the food will be prepared in the dining hall. That is how the difficulty which the time at which the asynchronous signal has come, Atithi has come, they will be able to handle it through two flops minimum. Okay, so this is just to clear the concept, and I'll go a little bit on the Atithi thing. And here, if you see, this is the full moon, this is the new moon, and the full moon. So this is the calendar year as per the Tithi, and we will see that each time it flips one at a time. Okay, these are the numbers of the Tithi. When it becomes 15, that means like the month is cut into two parts, and then full moon, new moon, full moon, followed by the new moon. Like that, the time will be moving on by the Tithi. Okay, we will see more in the next slide. I want to give you some brief visual experience of the Tithi. This is represented here. But it will, as the moon moves, then different Tithis will be mentioned. And there are, in a lunar month, there are 30 Tithis. And the distance, angular distance between the moon and the sun, which is which it shifts every time, will be 12 degrees, and this is called one tithi. And when one tithi ends, the another tithi follows, and these are all the different rasis or zodiac sign which the sun moves, and this is divided into 12 parts, and these are called different constellations. This will be divided within the great circle. So it will be a good representation about how it moves, and each time it moves, Tithi moves here, then this will also be moving. So now will be seeing how it moves from Meera Rashi to Mesha Rashi to Vrishaba Rashi. Okay, so we'll be seeing that. One Rashi covered, one more Rashi is covered. Okay, that is how two Rashis have been covered, and each one Rashi to another Rashi, you will find that there is one, say from here to here, there is one lunar month. That is like one Shukla Paksha and Krishna Paksha. Two things will be covered like that. Each this one whole thing happens 1 month, 2 month, like that. 12 months, it is 360. Okay, there will be slight variations. That is why Tithi will time also will be moving from 19 degree 19 hours to 26 hours, and the average of that is 24 hours. So that is how the Hora has come into play, and from that became the day duration later on. As I was mentioning, this asynchronous signal, when it comes here, it needs to be synchronized before it is fed to the another clock domain. So this is the inbuilt internals of the synchronizer. So here, this asynchronous signal is fed here through the first clock. Then whatever metastability happens, that this flop will be taken through, and then it will be a clean signal will be fed to the second flop, and both of these two flops of the synchronizer will be synchronized by the clock 2 domain. This is the destination clock domain. Okay, this synchronous asynchronous signal is coming from the another clock domain called clock 1. Okay, so now we will observe a little bit here. So if you see here in this destination clock domain, if the asynchronous signal is maintaining the setup time with respect to the destination domain, and also maintaining the hold time of this destination domain, then actually there is no need of a synchronizer, because the signal will be properly handled by this clock 2 domain flip-flop. That means, like, assume that Aditi gives enough time for the householder where he will be visiting and staying appropriately, then there is no need. The householder will be able to handle. So this is not an issue. Okay. For this, we don't need to add a big synchronizer. Even if we add a synchronizer, things are not going to break. Okay. Now coming to the next one. Assume the asynchronous signal, instead of giving enough time to the destination clock rising edge, assume it is coming very close to this one. Now what happens is like the signal is coming here and the synchronizer first flip-flop will have difficulty in following this asynchronous signal, processing the asynchronous signal. So what happens is, compared to the earlier case where the clock to Q propagation delay, which was earlier in the previous slides, was better. In this case, it is very low. That means like it is now clock to Q delay is more than 10% of its uh, mm, earlier delay, where it was successfully processed. So now it need not be in this fashion. Sometimes what happens is like it will be going in this one, continuously staying. After a certain time, it will be reaching. Okay, and it will be taking very long time here. Sometimes it will be keep on going, and then somewhere it reaches. So these are all different things based on the how close this edge is to the this asynchronous signal edge is to the destination clock rising edge. It need not be rising edge per se, but for simplicity we have considered the rising edge flip flop. So now if you observe now, uh, fortunately here it's still for this, that means like this is the Q0 signal. Now that will be the input for the second flop. Now if you see the there is enough setup time meeting for the second flop, hence the Q1 at the output is processed correctly. After this clock edge, it has processed, and this clock to Q delay is less than 10% acceptable limit. Okay, so even that means like synchronizer here, what it has done is like even though the signal came very close to this one, the clock to Q delay is more than 10%, which means it is a failed case. And the uh, second flop was able to handle and then catch the asynchronous signal correctly and was able to give a synchronous signal for this next flop in the another domain, which is of course same domain as this one. So now this signal, since it is synchronized with this clock, it will be able to easily process and it will move forward. So this you can see how the asynchronous signal has been properly captured. Okay, and this waveforms of this metastable condition of this will vary. Okay, sometimes they will be moving in the very long in the middle path and then will reach. Okay, sometimes vary in the middle path, reach the bottom. Okay, there will be multiple ways of this asynchronous metastable behavior will happen. Okay, that is this one. Now we will consider another situation wherein the asynchronous signal here, this one is coming very close to the destination clock edge. Then what happens is like that means like it is so difficult. This activity is just coming when the householder is about to eat lunch. Then it so happens that it will miss it. It will not be able to capture. Okay, because now it missed, so now the Q1 will see it as 0. As such, if you see here, if you see there is some delta lag between them. That means like technically speaking, this asynchronous signal has come before the rising edge. Okay, whether this rising edge need to be processed or not is a different thing, but it to just as far as the checkbox is concerned, he has come earlier to the rising edge, and it is at the output of the synchronizer, it has figured out that as no person has come. Asynchronous signal has not changed to logic high. It will be fed. So this is called a failure. So it will be represented by the synchronizer. Reliability is represented by this um, constant called MTBF. Okay, mean time between failure. Okay, that means like this is a reliability concern, and it means like how often this synchronizer will fail. This is a good metric with which we can say that whether the synchronizer is optimal for the these two clock domains. So it is represented by this equation. Here the FC belongs to the destination frequency, and this FD belongs to the asynchronous signal data rate. This signal asynchronous signal data rate, and uh, tau represents the time constants of this flop. Okay, so and tr belongs to the resolution time, and that means like how long this there is time. That means like it is a little bit complex one. I'll not go too deep into it. There are other videos from net, you can see it, and there are very good papers, IEEE papers, which you can read. They are, some of them are quoted in the reference material. So based on this MTBF, you will know that whether what type of, based on these frequencies and aperture width. This TW means aperture width. Usually you can take as setup plus hold of this flip-flop. Okay, so based on that, we can calculate how much is the MTBF of this synchronizer. It is, if the MTBF is not high, then we need to add more number of stages here. Okay, so we will figure out some details on why synthesis tool could not add the synchronizer even though it knows some of the information. That means like from the chip design constraint, it is known that what are these frequencies. It knows it. And it also knows what is their duty cycle. All that it knows. Uh, and it also knows what is the PVT associated with it and which is the worst case PVT also it knows. And it also knows how many types of synchronizers are offered by the IP library and what is their area, what is the leakage, and the MTBF information is not known to it because there is no specific attribute which the synthesis tool process. However, it can be provided as part of a file, which is currently it is not as per the standard, but it can be provided. So based on all this information, you can say that some information is known. Okay, so what happens is like then why it is not able to predict the synchronizer. So to go into that one, we will know little bit in the other slides. So if you see the clock domain crossing information, and the synthesis tool does not know a few things. So we will come to the ASIL in the next slide. So here it does not, even though it knows there are so many cloud domain crossings, and even though it knows number of CDCs in SOC, I am saying that there is still the amount of data it needs to process and the amount of the calculation of the worst MTBF possible, that is slightly beyond the thing. And one more thing is to calculate the MTBF of best synchronizer, because no, usually the IP library will provide the destination frequency, and it will also provide the PVTs associated with it, and it will provide some slew and tau information, resolution type constant information. but for different clock domains with different frequencies it will not provide. So in that case it has to use the data available by the IP data sheet, and it needs to extrapolate and figure out what is the MTBF of the synchronizer which should be placed in between the cross domain. Aside to that, to figure out whether it is the best case is FIFO or best case is another type of configuration using handshake mechanism, or through other Gray counters, or through flip-flop series synchronizer is the best one. So there are variety of means, like even in flip-flops based on two or three flops. So that one and all depends upon the various calculations synthesis needs to do. So that much is actually beyond its scope, because its synthesis main job is to translate the RTL code into gate level content. On top of it, doing this one, which is a reliability aspect, which is beyond its capability. So it will not be able to do. Aside to that, we will also discuss how and why it cannot do the ASL aspect also. In this, we will figure out why synthesis tool cannot figure out the ASL related to the product specifications. In the sense like how to ensure the fail safety and the amount of failure rates, all these things, why the tool cannot predict. Okay, actually in simple sentence it is not easy, and the whole thing is way more complex. Okay, so let us do a little bit dig into what all the aspects are related to it. So if you see the ASIL standard of the product, so the product, let's say whether it is an aerospace product or an automotive product or any industrial product or anything, the product has to meet some safety criteria, so that the customer trust will be high, and the, production doesn't get into serious issues really, and any human loss or any sort of loss as such. Monitoring is also a big thing. So coming to that, ASIL stands for Automotive Safety Integrity Level. This is a risk classification system defined by ISO 26262. Okay, this is basically to ensure functional safety in road vehicles. And as we know, there are variety of chips which will go in different parts of the vehicle, either it is an aerospace or a vehicle or a auto motive vehicles. Okay, so some of these chips might lie within the tail lights, where the risk is low, and some will lie at the braking of the wheels. So this is very risky. So some are low risk and some are high risk. So based on these things, how we will figure out the various aspects of it, the ASIL and all are very crucial. And for that, ASIL depends upon what is the exposure, and that will like probability of exposure of this failure. It will also take into consideration the severity of the failure and how much controllability it has. That means like it is not controllability of the chip, it is basically controllability of the driver. Okay, so of the vehicle where the chips are included. Okay, so if you see the exposure means like it has variety of classifications starting from E0, which means incredibly unlikely, to E2, E3, E4. So high probability of happening, which might result in any injury, loss of life, or anything. So this is one classification based on which we will know that the failure rate is very, very crucial. That means like here it is shown like if the chip is used in low demand mode or in high demand mode. So these are the failure rates observed per hour. Okay, so and if you see this is based on the safety integrity level, and this automotive safety integrity level is slightly different. Their nomenclature is also different, and roughly we can map it to in this fashion. Okay, there is nothing for 4. So if you see here, the ASIL failure rate itself is very, very low for the worst case like D. So what is this failure rate means? Like when we have observed the MTBF, it is the inverse of MTBF is the failure rate. Okay, so failure rate is not only related to one CDC synchronizer or one RDC synchronizer and all, it is for the entire chip. Once you take the chip, when the automotive system is failure rate is being analyzed, it needs to account all the other components involved in the automotive vehicle. So it needs to compute, and for that you need to use the 1 by n equal to 1 by n1 plus 1 by n2, like that 1 by nn. So those kind of methods to figure out what is the uh, lowest failure rate. Okay, so now these failure rates will determine based on this how many number of CDCs exist, and based on that we need to figure out what is the MTBF of the synchronizer. So I'm just giving a clue that to compute that one, that too considering different frequencies, it is beyond the scope of the synthesis tool. So what I want to mention is like assume there is a very good blacksmith. We cannot expect him to do as good job as a shoemaker does. So this is the amount of complexity. So that much the synthesis tool, what it is supposed to do, it cannot do this much. And coming to the another one, severity. So severity classification is S0 to S3. S0 stands for no injuries, and like this. And for S3, it is life-threatening to fatal injuries. So one needs to figure out that when there is a probability of failure, what is the severity? Now comes the controllability aspect. So that means like what is the controllability exists at the person who is driving the automotive vehicle. So if you see here, C0 stands for controllable in general. C1 means simply controllable. C3 means difficult to control. So based on all these things, one should predict what is ASIL. A stands for what is ASIL, C, B, D, like that. So if you see here, ASIL D, it is a combination of S3, S4, S3, this one, and the E4 and C3. Okay, so all these things if we need to consider as part of the ASIL-D classification standard, and that is why this is the most pessimistic scenario. So considering all this one by synthesis tool is next to impossible, or at this point of time it is not ready yet. Hence, the synchronizers are not inferred as part of the synthesis tool. Yeah, with this, I'll conclude this presentation. Thank you.